Good morning. Savdut says let's not, penalize the folks who have made it early, right? We'll penalize the folks who come a little late, right? So myself, my name is Mario, and along with me today, speaking some part, would be Sachin. Both of us are from the Spark Technology Center in India, right? This was a lab that was set up about 2 months ago, right? And we work out of it. How did we come up with this topic, right? So I think 2 meetups ago, it was in December, that the team presented a deep dive on Spark streaming, right? And when you did that, some of the feedback that we got from that meeting was, can you do a comparison of the various streaming open source projects that are there, kind of a thing, right? So that was one of the requests. And because of that request, this topic is here. So the good way to look at it is we take your feedback, right? And we are working on presenting to you what you guys want, right? So these are the topics or the agenda that we will go through today, right? We look at streaming analytics, the system architecture, because we have a wide variety of things that we're looking here. Things like, Storm, Trident, Flink, and streaming. So we'll just set the base up with, the various 2 architectures basically that we have. We look at, what are the features you're looking at when you're building out a streaming application. Compare them, those features against all this, kind of sum it up, and then Sachin will actually walk you through, some of the benchmarking efforts that we've been trying to do with Spark streaming, right? So before I start, let me take a poll of hands. How many of you are repeat audience for this meetup? Oh, most of you are repeat. Very good. How many of you have? So I won't go on to ask how many are new, because I know how many are new. How many of you have actually used, let's say, Storm or Trident? Okay. Put it in production. Okay, but you've at least written an application and tried it out. Cool. So mostly that's just about 2 or 3. I'll ask about Flink. Flink is pretty new. Anybody played with Flink APIs for streaming? No one. Okay, good. So I'll not ask if anyone has put Flink in production. Okay, so that's good. At least I know the audience and where I will concentrate on. Okay. So the way we'll do it is I'll try to finish up to here before we go for our lunch break, or not lunch break, our tea break, coffee and samosas. But if I tend to go far, then we'll break somewhere early and then come back, and then we'll do this. And you can ask questions anytime. Feel free to stop. You can also ask questions at the end. At the end, we'll have a Q&A also. But at any time, just stop and ask. Right? So this is a very simple slide. The reason I added here is not that I'm giving you, something great, but I just wanted to set it up for the next set of things that we'll get into, right? So what's a streaming application? A streaming application, let's say, as compared to a typical, batch or historical application, is that you have an event source. You're getting events from that. You collect them and you process them and then you write them out, right? Most of the time with streaming is you're getting data at such a high rate that you don't want to actually store it and then run queries on it, right? You want to process it as it comes in, keep it in memory, because time is a clear importance or the main essence there, right? You don't want to store it and then after a long time, get that information or the insight out of it, right? Okay, given that we know this, I will then step into the various streaming systems that we are talking about today. The 2 kind of architectures that are there, right? So this is what we call the continuous operator architecture. The other way to look at it is static scheduling. So I showed you in the previous slide, we have a source, we have a sink, and in the center you actually had your processing logic, right? Your receiver that's receiving data or your computation on it. So what happens when you use a continuous operator architecture is basically, so let's say this is one node on which your source is running, right, receiving, and this is another node. I made it actually, let's say I have two processing steps that I do, right? I'm doing some, let's say, some filtering in one, and then I'm doing some aggregation, right? And I've actually parallelized it, so I have two instances of these running, right? And two instances of this, so data comes in, it flows. In the continuous operator architecture, what happens is, let's take for simplicity's sake that each is a separate node. So there is a dedicated processor, a process running on this node that is continuously just receiving data from here, and this guy is receiving data. So data comes in, right? This guy is just waiting for that data, the message gets passed to him, he processes it, writes it up, right? So that's why we call it a continuous operator. If your code here is an operator, it's continuously, all it's doing is, there's a buffer that's transferred between these guys, right? So it's just the buffer. It's not like, as I'll show you on the next slide, right? Compared to a task scheduler. Now in the task scheduler, I do have long-running processes, but it's not just that, the data buffer is being shipped from one guy to the other. What happens is your program, in both cases, your program can be a, directed acyclic graph, but what happens here is, in the task scheduler mode, I break up your program that needs to run into a set of tasks, and those tasks are distributed to the workers, and the worker has the data already. It's not just a message that I'm shipping to that guy and that guy is writing. So there's no continuous, on the nodes, a program that just, or a snippet of code that's reading data off a buffer, processing and sending it, right? So here what happens is, you break it into tasks. The tasks decide what's the next, the task, the guy sitting here decides what's the next set of tasks I need to run in your program. And then he calls the task scheduler and says, schedule these tasks. Wherever it runs, you assume you have threads there. When I actually run that, there is some amount of data locality, so I'm not pulling data over the network, right? So let's say the data is local there, right? The computation happens, and the results come back here to this guy, right? So those are two models that I talk. Why I'm talking about this? Because of the list of systems that we are talking about today. Some of them, at least Spark streaming is based on this. It's actually a task scheduler, right? So Spark was built as a batch system, right? And so it does this task scheduling, right? Compared to MapReduce, it brought down processing or scheduling time so low that I said we can even do streaming on it, right? So it still has this, what I call a dynamic streaming, dynamic task scheduling. Whereas if you look at the previous one, most of the systems that we are talking in comparison to, like say Storm, Flink, Trident, right, are all continuous operating, right? Streaming, Spark streaming is the only one where it's task scheduler. So what's the pros and cons, right? When I'm talking at a very high level, right? So if I had a continuous operator architecture, and I'm not deep diving, I'll say, if I just look at it and say, I don't need, every time I have a job to do, I don't need to do dynamic task scheduling overheads, right? Figuring out where to send it. Because I've already statically figured out the layout and the message, it knows where the message needs to go next, so it's just the message, right? In a task scheduler architecture, you probably have, dynamic task scheduling overheads. The question is, how big or small that is, and we hope it's at some small level. But one of the benefits that you can have is, let's say I have dynamic data, right? Each time data is changing and the amount of partitions I have is changing. Then this guy, because he's doing the scheduling dynamically, I can actually run it in more parallel, right? Whereas this guy, once he starts up your program, he already has those fixed nodes, right? And suddenly if you have a sudden surge of data, or your data itself is not partitioned well as it's coming out of one of those source nodes, you'll get a whole lag in your entire processing workflow. Whereas this guy can probably, since he's doing it at runtime dynamically, he can adjust for that, assuming you have more, compute nodes available, kind of a thing. And that's one of the benefits that you would, say that. Spark streaming till actually what's out there 1.6 couldn't, though if you're using Spark, just say for your normal batch, it would do dynamic allocation, right, based on that. Spark streaming in 1.6, there are reasons why it didn't use that dynamic allocation feature, right? So this point that I'm talking about, you could say is a moot point. It's just theoretical. Spark Streaming doesn't exploit it. But in 2.0, for Spark Streaming applications also, the dynamic allocation has been, set up. So once you go to 2.0, you can actually take a benefit of this feature that I'm talking about. Okay. So you guys wanted like a comparison of the streaming systems, right? So what I thought I'll do is I'll go through a list of what we think are important features that you would need for a streaming application. I'll first explain what those features mean, and then we'll look at each of the systems, how they match up to these features. All right. A note of caution about when you compare two things, especially if you do benchmarks, right? Benchmarks are very tied to your workload, right? So in the world, I believe there's no one system that fits all, right? If this is your workload, on this you might get something, on that you might get. That's one thing. We're not showing you benchmark numbers at the end, so I'm happy that we don't run into that problem. The other problem that I could think of is, if somebody comes and gives us a talk about comparing these systems, and if he has used both those systems in production, then that's the best guy you want to talk about it, right? So if you go and look at YouTube for this topic, you would see a bunch of architects from Yahoo. I think Tom and Bobby have given. So those are guys who are actually running production systems with, say, Storm and streaming, Spark Streaming, right? So you're getting it from the horse's mouth, right? In my case, or in our case here, we are not yet at that level, right? So take that with a pinch of salt. So therefore, I try to go into things of just talking from a theoretical perspective. There is also some practical stuff, but not from an experience of, I did this with these two systems in production and this is what I saw, right? So we'll keep it at that. Okay. So the first thing that I said is important for a streaming application is fault tolerance. So what's message processing guarantees, right? I think we talked about this two meetups ago, but I'll just talk to it. So you're getting a stream of data, and you want to ensure one thing, right? I don't want to lose data. I want to process every data, right? But can you also guarantee me that when I'm processing it, right, apart from losing data, that the same data or event doesn't get processed twice by the system, right? And the next level is saying, can you guarantee me exactly that each event that comes in will be definitely processed only once by the system? So let's say I'm doing at the end, I'm doing an aggregation, right? I don't want to do duplicates because then my result is double, right? And then the streaming, each of the streaming systems that we talk about will have various of how they support this, right? So the first thing is that the simplest one is called at most once, right? Here what they're saying is, I might drop messages, right, if something happens, but for sure the system will not process a message in duplicate, right? There is the next level that says, at least once, right? You will not lose data, right? But you might end up processing one event twice, right? The most stringent of these are exactly once. So you're saying that I guarantee you one event, there is no loss of events, as well as one is processed exactly once. So when you go to a streaming system, I talked to you about the source, the processing, and the result that you're writing. So for these attributes actually build up on each of these individual components that you have, the three components that you have in your streaming application, right? So if you want, exactly once processing, you kind of need, your source needs to be like a reliable source. What that means is, I get a message, I can acknowledge back to that guy that I got the message, right? And if I don't acknowledge, he can actually replay it back. I can go back and ask him, give me the data back from where I last acknowledged to what I received, right? So if you don't have a source by which is reliable, then it's really hard to do these stuff. So it depends on how your source is. Now how people have worked around this problem is some sources by default allow this reliability, right? You can acknowledge and they have persistence and you can go back and ask them to replay, right? There are some sources that don't have that reliability, right? So most of the architectures that you look, folks introduce a message queue before my real source. Like I use Kafka. Let's say I'm processing data from Twitter, I put it into Kafka, and then on the other side I'm actually reading off Kafka. It's a message queue. And with that you automatically get the source becomes reliable for a small penalty that you pay for actually processing that data inside Kafka, right? And Kafka gives you storage persistence. So most of them do that today, I would say, right? Because you get reliability for a small penalty for actually storing it in there, right? Processing. Now this depends on whether your streaming system itself can guarantee you that once you've ensured that the source can handle that, or how I get messages from the source is reliable and I can replay to. Inside my processing, those modules can, whichever system that we have, guarantee that I'll process the data exactly once, right? Things like Spark streaming, not Spark streaming, but Spark itself, the RTD is built on a model where there's exactly once processing, right? Forget about Spark streaming. Spark RTDs guarantee you that. So then automatically you get that. So then you go and ask, with Storm or Trident and Flink, does that system itself give you that, right? The third thing that happens is the sync. Let's say, in case of some systems like Spark or even Flink, I could do some aggregations and keep that data inside Spark itself. I don't need to go to an external store, right? I can do a map with state or reduce or some kind of aggregation. So then automatically, since this is exactly once processing, even that happens. But what if I have to write to a destination which is an external system, right? Let's say I'm writing to a relational database or something else. I need to ensure that even there it's exactly once, right? And what happens here is, in that case, you really need a sync that has atomic capability, right? I can guarantee, much like a relational database, it's a ACID capability, atomicity. If you have that, then you can implement it, right? Some of them make it easy to implement. Some of them give you for some of these destinations. For some guys, you are responsible for ensuring that atomic write capability. You roll your own code for that. Okay. The next important thing in a stream, yeah, you have a question.
In the next slide.
Yes.
The processing step, it is obvious.
Sorry?
The processing step.
Yes.
It is obvious that it will be automatic. Processing is not automatic.
No, it's not guaranteed. We will look at it, right? So, let's say for instance I'm flowing data, right? And somewhere in between one node went down. So I had to restart that node, right? So the upstream processing, downstream, what did the whole system as such did, right? Can it guarantee that half the processing happened, that when it replays, he is replaying correctly? Or some of those nodes would have, some of the upstream nodes would process that data twice. All that boils down to fault tolerance, right? If my system is running well, right, I wouldn't bother about processing, right? Everything is going through fine. But as I said, the message processing guarantees are tied to fault tolerance. One particular node that was receiving data, right, in my flow went down. That's when we say what happens on your message processing guarantees, right? For a normal system that's working, that has nothing, you don't worry about exactly what, right? Yeah.
So I understand with the 3 points which you have emphasized on, like only once processing, exactly once processing.
Yeah.
Is it that each one of them has some, like source has some sort of responsibility and the processing engine has some
Yes,
sort of responsibility?
exactly.
That's
Yes, that's what I'm trying to say. So I'm saying if you don't have a source that's reliable, obviously, here what I'm worried is end-to-end processing guarantees. An end-to-end processing guarantees is depending on the guarantee of each of these 3 guys.
Right. And one more point, like you mentioned about the dynamic data partitioning,
Yes.
where Spark streaming has like has
Or don't have.
the basic
Yes.
the basic way of processing
Yes.
of Spark streaming is based on dynamic
Yes.
data processing.
Yes.
So I understand that if you have some queues, so if you have some a good amount of processing, complex processing, then it would be advisable to get into dynamic data processing. I'm just asking, which is the best use case of getting into dynamic data processing? Like, given a chance, if you have been asked for a certain use case, which like which processing or which tool?
I think at a very high level, if I were to say it, would go back to those pros and cons that I talked about, right? This basically, where is that? This one was basically at a very theory and not going deep down. I was saying, because I don't have at each step task scheduling overheads, if I wanted very low latency, then it seems to me that this should give me that benefit.
Yeah, that's basically
Yes,
real
exactly.
time, and this term as the near real time.
Yes, and it depends on how much can you cut down this, right? If your latency you're looking is lower than what the task scheduling requires, obviously you have a problem, right? The question is, can you cut this to a minimum as possible, kind of a thing. So to me, to jump ahead, right? If you want to use Spark streaming for real time, you really need to get the task scheduler to be as minimal, overhead kind of a thing, right? That's the question.
Thank you.
So when we talk about the source should be reliable, what is
Yes.
it? From where we are getting the data or inside the Spark architecture itself? And
From where I'm getting the data itself.
so,
Let's say, for instance, because I talked about fault tolerance, right? So some node went down. Let's say the node, I had a receiver, guy was receiving data, let's say from Twitter, right? And Twitter is not reliable. And say that for some node, that node went down. Nodes will go down. Then what happens? By the time that node came up, have I lost that data? Can I get back that data? So if you have a source by which you can't get back that data, you have a problem, right? You're going to lose data. But if you have a source by which I can go back and say, replay that data to me, then I have a reliable and durable source. So if I put that, what I was saying is if I put that data, let's say from Twitter, I put it into Kafka, with Kafka, you have that reliability. I can go and say, give me, so what happens there is each message that comes in is assigned an offset. And when I'm receiving it, I know what offset it is. An offset is a serial number. So if I know I processed 10th message, and then my node crashed, and it took me 5 seconds to bring back that node, theoretically speaking, I can still go back to Kafka and say, Kafka, give me the 10th message again. Can you do that with Twitter? Can you go back to Twitter and say, give me the 10th message? Obviously not.
so just like a message queue which is holding a message, if something happen on the
Yes.
return node.
Yes.
So
And you want a message queue that's has very low latency, right? Obviously, we started with you saying in a streaming application, the reason you do it streaming is that you want to process it in real time. So if that queuing system is going to take ages to store it, and then you have lost the point itself. But most people are finding that with Kafka, I'm able to get that. So what they really do is put a message queue in front.
So the reliable source here doesn't mean the transport layer or reliable.
The ability that I can acknowledge back to that guy that when I had a receiver, I received a message. Normally you can say, I acknowledge to that guy I received this data, okay? Or even in worst case, you can go back and say, give me back data from a particular point.
So the Kafka does this, opposite thing, it informs the Twitter node, suppose we have the Twitter node.
It depends on how you write it, right? So one of the things is, one way I will tell you is that, let's say I told you about the offset, and right? Your Kafka client, you can actually have this ACK. So when you receive a message, you say ACK. So the Kafka client now knows that the actual producer till what message he got and what he has processed, right? And can replay. The other thing that Kafka also allows you, if I don't do the ACK, and I'm tracking the offsets, I can go back and ask him for, give me this message with this offset, and then start asking for message from there. Obviously, the question is, you have enough persistence in Kafka to give you that. Let's say I process 1 day's data. I think by default it's like 7 days, but you wouldn't store for 7 days. But let's say I put my Kafka's persistence of messages for half a day, right? And a half a day I processed, and then after 13th hour I went and crashed, right? And I go back and ask Kafka for data from 13 hours ago, obviously he doesn't have it, right? He'll give me 12 hours data, but he can't give me 13 hours data. So what you want to go back to and replay from, obviously you need that much persistence. In normal, you want a system where, and we'll talk about it in the other one, where, I think in the other point, where if I'm storing state in the system, can the processing system itself guarantee that it doesn't lose that state across a failure? Then I don't need to go back to Kafka so long. It's such a small window by which I have to go back to Kafka. But I just use 12 hour, 13 hour just for, to bring out the example for you. Yeah.
What happens when we are not getting data from source because you are streaming context? It keeps creating batch or window, right?
Yes. Yeah.
Means your D-stream.
Yes.
Suppose it's not getting data from source.
Yes.
What will happen in that case in terms of Spark streaming?
Okay. So it's very simple. So there's a time window and you basically cut it and you get it, right? So now you have an empty RDD, right? So let's say you're processing, the simplest case is you're doing a map. There is nothing in the map. The map doesn't flow, right? It's careless, nothing. So nothing happens.
So that D-stream will be created with empty...
Yes, the D-stream is created, the D-stream doesn't have, so your processing is doing a map, it's doing a filter, it's as efficient because there's nothing to loop. Right. Okay, we were at back pressure. So a streaming application, as you figured out by now, runs 24/7. You don't run it, stop it kind of a thing. So when you run it continuous, obviously things are not going to be static, right? We talked about nodes that fail, right? Something not failed but became slow. I don't know, I was writing to a destination, that destination was a database, something happened on the database, writing is happening very slow. It crashed. The other problem could be that suddenly I got a surge of input data, right? What happens now to your streaming system, right? Some streaming systems might not do anything, right? Does your streaming system does anything? Worst case, it might just drop those messages because I can't handle it, right? Let's say the source. The worst case could be in your whole node, all your buffers start getting filled up so much that at some point actually you might crash, right? Let's say even you have handled this. This doesn't happen, right? So I have a system that actually, going back to my message processing guarantees, right? It will replay the data. Let's say a node became very slow or actually went down, and the other nodes have not yet detected it, so they try to send it, right? There is nobody to receive it till another guy comes up and message is routed to them. What do these upstream components do? Because they have to replay it, because the master or the job manager will ask them to replay it because some guy there is not receiving it. What happens? The upstream components, will they simply keep repeating the same work? Because I had 3 steps, right? At the 3rd step is where data is getting lost. And then the system says, oh, 3rd step got lost, replay, because you wanted at least once or at most once or exactly once, so it has to replay. So these upstream guys are simply doing the same computation over and over again because some guy down is there, right? Or the message is getting lost, right? Or can the system actually kind of detect this and do something about it, right? Can I automatically slow down the upstream component? So if the upstream component is doing some processing and the downstream component is writing to a database, the database becomes slow, I theoretically want to even slow down the processing speed of the guy who's doing the processing, right? So the whole system stays stable. There are multiple ways that this gets done, right? There is a spec called reactorstreams.org. That one way they say is that the downstream components actually send async messages to the upstream components saying slow down, right? That's one way. Spark streaming does it a different way because he has different kind of data because he's batch, but he does it, right? Some other guys in their automatic way, when they flow buffers between each, they have a high level watermark of how much I can fill the buffer. Beyond that I won't fill. So the buffer has to get freed and only then I'll fill. So there are various ways by which systems deal with back pressure, and in our comparison there are a few systems that do nothing about back pressure, so obviously you have a problem with those systems, right? So this is it. The next thing is more like for an application programmer, right? Is the streaming system stateful or stateless, right? Or is one aspect. So here the logic is, let's say, I'm doing some summation or aggregation by keys, right? And I want that data there, right? Let me go back. Okay, my slide is first talking about built-in primitives and not stateful versus stateless, right? So built-in primitives, right? If I wanted to do things like, join, I'm getting data, I want to join it with some other data, right? I'm getting two streams, I want to join those two streams. Are there built-in constructs in this, from the API of that system that allow me to do that, or do I have to write my own code? Right? Systems differ like that. I'll give you an example. The most common thing that you do in a streaming application is windows, right? Because you're not going to process data infinitely, because a stream is infinite, right? You normally cut windows and you process. So if I wanted to do windowing, right, does the system provide me enough API constructs to do the windowing by just calling an API versus me writing the code to actually do the windowing functionality? The other thing is, like, if I have a window, right, can I dynamically trigger, the default could be, a window could be based on time, say 5 minutes, right? But if the amount of messages increase within that 5, can you actually trigger me, right? So, does the system even give you that kind of? This was the other one, stateful versus stateless, right? So you get each event and you're processing it, and then you're doing an aggregation, across those events, right? Again, does the API allow you to do it, or you write that yourself, right? Is the question, right? And then also when you go to stateful, what happens when I asked the question there, when one of those nodes went down or some of the nodes went down, what happened to that state? Do I have to really replay, or you have a copy of what was last saved and only from that point you start again? There's another point that talks about what people call lambda architecture, right? Today when you're building systems, people need to do, I have data that's coming in, I need to process it in real time to get some insights, and then I also have to process it in historical, in a batch system, right? At the end of the day, I still do some computations, right? And many of the calculations that you would do would be very similar, just that you're doing it in real time and you're doing it at the end of the day, right? But you obviously want to ensure that both are matching. What the insight that you came out in real time matches what you did. Now, if you had two separate systems to do this, obviously you have to write different logic. The code to implement, your algorithm has to be written in different APIs of different systems, and most likely, this is over a period of 6 months, let's say, 2 different people working on it. You did one aggregation this way, that guy did it a different way. Soon there's a sync or a dissync between those codes, and what happens is the insight that you're getting real time doesn't match what your historical insight is, and then you have a problem. Right? Most people face that. Would it be nice, basically, if I had a single system, or the code that I wrote, or some part of that code that I wrote for both the logic, I can reuse it across each, right? Do systems provide this? This is what they call lambda. Now systems claim this. Before I get into that, there's a lot of debate on this, right? If you look at one end of it, leaving these streaming systems, there's a spec call or an SDK for streaming and batch called Google Data Flow was there, which has now come as Apache Beam, right? So typically, folks like Spark Streaming said, look, what you get is an RDD, and RDD has 10 APIs. You get a DStream. DStream also has 2 APIs, and then you can say for each RDD in that DStream, and you have the same API, and therefore, you can write the same logic, right? There are papers out there that where Google Data Flow specifically beats, or Apache Beam beats up on Spark Streaming, saying, hey, it's not that simple, right? Let take a particular use case that they had in Google, and they did this in batch, they did this in streaming. Now let's write it in my Data Flow SDK, and let's see what's the similarity of the code. Let's write it in Spark Streaming and see what's the difference. And they're showing it's not just as simple of having an overlapping API. It needs to go beyond that. Right, I'm not getting into detail, but that's also there. So I'll actually boil it down to rather say a single implementation. Do these systems have overlapping API for stream and batch? Right, keep it slightly higher level. Right, that's one. The other thing that is when you're looking at something like streaming, you have a whole platform, right? So I can, like in case of Spark streaming, right, or even Flink. It's not just the streaming application, right? The other features that I have, I can take my stream, make it into a data frame, de-stream, I can write SQL on it, and that kind of a thing. So those also is beneficial when we talk about this API. Apart from even it's the same logic that I have for both. There are two things I have in one slide. The question is, when you have these streaming applications and multiple of them, can you actually share them well over the existing cluster that's also running different other kind of applications on that cluster? So the question is basically resource utilization, right? Everywhere everybody wants to ensure that I don't want a dedicated cluster for each job. I have a cluster, and each application on that is going to have varied processing requirements over a period of time. But I want both of them as max to utilize the same cluster for these, right? In that case, can whatever streaming system that you're using, ensure you can do that, right? And it also points down to, whatever is your scheduler, resource manager there, can you actually allocate up ahead for each of your processes a fixed amount of, processing memory or whatever? Can you do it at that granular level, right? Okay, so this was the background of what's important for a streaming application, and then I'll actually go into looking at each of these streaming systems. I've already taken 40 minutes on that. So what I'll do is for the next 20 minutes try to complete as many of these systems and then cut, and then we'll come off that, right? So I said let's look at Storm. Right? I had a snippet here, so you don't need to go into that. The question for me is, I as a techie guy, when you show me something, I always say, show me, do you need me to do that before I go ahead, or you don't need to look at code kind of a thing. So what do you guys want me to do? Dive in a little to the code? Okay. Okay, so this is the Storm model, and so I will not do this for Spark streaming. Reason, because 2 meetups ago, we had a deep dive on Spark streaming, right? So if you are, most of you said you attended those. So if you have not, I won't go into this level. If you need this level for Spark streaming, please go back to our meetup. The video is there, the slides are there. You will get that information, right? In the interest of time, you won't do. So we talked about a source, a computation, and then a destination, right? So that boils down here. Let's start with this. You have something called you build out, which is a topology. What I said, what the various nodes and processing. So you start with the topology. The source is called a spout in Storm. So this is just giving a name. I'm calling it Twitter sample spout, and I give some Java code implementation that implements this guy. So what this guy will actually do is, inside this code, he has a nice interface where you read data and he'll call next, so you give him the next tuple that happens. I'll go into that if you want. The next part, once you do that, any of your processing logic, right, is called a bolt. So you have spouts and bolts. Spouts are the sources and bolts. So now if you see here, I'm saying I'm creating a bolt, but the most important thing is I'm tying this bolt to that spout. See, I named this spout as Twitter sample spout, so that's how you tie your pipeline kind of a thing, right? And this guy is called the word splitter board, so I actually have logic inside this interface that will actually split the messages by word, right? Then I have something called a filter. I've not gone into it. That again, you see that this guy was word splitter, and word splitter fed into ignore word boards, where I did some filtering, assume, and then I actually did a counter. And the counter again took from that source. So now I've actually built my pipeline, kind of a thing, right? And then finally, you build this, and then you create a cluster. I think this was a simple case where he's creating a local cluster, so you want to run it on your local system, and then you submit this this topology, right, to the cluster, right? So that's the kind of flow, and then when you submit that, he's going to obviously compile your program. It might be builds a directed acyclic graph. I don't know Storm internally, but I assume he does something like that. Decides the layout. So at each of these levels, you're seeing something here called shuffle grouping. Right? Shuffle grouping is basically when I have multiple instances, you control how they should be sprayed, to parallelize the processing, right? There are various types of grouping. So if you look at the Storm documentation, you can do on random, or you could do, based on some data and stuff like that, right? So that's how it actually flows, right? I'm not going into actually each of these. I thought I would go into this and show you, that interface of, okay, how I set up, a Twitter reader or the Twitter 4J API, and waiting for data. Then, the the Storm guy will actually call this method called next, and in next is where I give whatever data I've got till now and put a queue and that stuff. Right? In interest of time, I'm not doing that. Okay, but high level, that is it. So what actually happens? So, finally once you submit, it actually builds out, the topology, which the class was called topology. It's nothing but a network of spout and poles, right? In this case, let's say I can also control a spout if I want n instances of a spout. So I want to even receive a parallelism. Right? Let's take, for instance, Kafka. Kafka gives you a nice thing of partitions. So the reason is, like, if you just have one receiver who's receiving data, you're obviously going to get choked by, there's only so fat that pipe can be, right? What if I could have multiple receivers? So the way Kafka does is you have a topic and you have multiple partitions. So the source guys itself spread the data across multiple partitions. And here, in this simplest case, let's say, this could be the same Kafka topic, different partitions that I'm reading. So actually at receiver also I have parallelism, right? And then this is actually saying your operator. And we said this is a continuous operator model, so you can actually take it and lay it on a physical node if you have, like this. Say these are running and messages are passing across these guys. And there is some guy who's tracking where the message flowed. If you want at least once processing and replayability, if one of these guys fails in between, the system needs to know from where I should restart, right, replaying that message and stuff like that. Okay. Oh, I missed the last thing. Let me go back, sorry. When I talked about here, I said some streaming systems, like Spark streaming are micro batch. They wait for some time, get some messages, build up an RTD of that, and then you process it, right? Storm and stuff like that, as each message comes in, each individual event gets processed as it. So the question is it really tuple level versus a micro batch, right? Yeah, so in Storm, you process at an individual message level. So your receiver receives data, and that the Storm guy calls him, says, give me your next message, and he gives him one message, and that message flows through your entire system. Right? It's true bad. Is Storm stateless? No. Storm by itself is not stateless, or doesn't give you anything built into it, right? So let's say I'm doing an aggregation. So let me example. I have a processor that, as we saw, that the word count, right? So he's keeping that word count with him. Now let's say that node died, right? When Storm brings back up that node, he doesn't have what his last aggregate count is. So he's stateless, right? You have to then replay from start, right? That's what I mentioned in there. Does Storm have built-in primitives? Does he have a nice API to do aggregation and stuff? No, you have to write your own. So you're getting data, you decide how to split it by keys, everything is your own, right? It just gives you a nice Java interface or whichever API you're writing, language, he gives you this interface and says, now you write all your code, right? He's not doing anything on top of it. So if you wanted to do any of this, you have to write that inside your bolt. Message processing guarantees. Storm by default will be at most once, right? He doesn't track. So I talked about you in the previous thing, is there somebody who's tracking where the message flowed? Okay, this guy never received it because he's not getting back. By default, you do Atmos once, he's not even tracking that, and he will never replay. You can actually set him up to actually do track and replay, right? But when you do the track and replay, he doesn't guarantee that duplication will not happen. So that's the problem, right? He doesn't do that. So you will get at least once, you don't get exactly once, right? When you turn on this, he might duplicate, replay some data in duplicate. The other one that this applies only to Storm and Trident is, can you run it on a shared cluster? Storm doesn't, in Storm the scheduler component is something called Nimbus. He can't run as a, as a Yarn application or a Mesos application. So in reality, you can't really get this guy to work on the cluster that is shared across different applications. And we'll talk about this something, even other, if I have n number of Storm applications itself, does this guy handle play well, right? I did see that Hortonworks allows you to run this distribution as a Yarn application, but I'm not too sure of it. The other thing was, so this was the architecture, right? So you have this Nimbus here. The way they coordinate how messages and each guy is up or down is both these guys actually, send heartbeat messages to the zookeeper, right? And then this guy tracks. So I said that when you say, the replay messages for, at most once kind of a thing, or the other one, he's tracking where, data flowed across these guys, and, that guy's gone down, he never hacked that message, and therefore I know where I need to replay. But this architecture is basically showing that in Storm, this Nimbus is like a single point of failure, right? In this case, let me go back. If the worker fails, each worker has a supervisor, the supervisor will restart that guy, right? No problem. If the supervisor fails, Nimbus will restart him, will detect that there's basically a keep alive signal that comes in here, so he will restart it. If this guy fails, there's nobody to restart him. Of course, you could do simple things like run there are tools like monitor stuff that is just monitoring this guy, and in case he goes down, restart him kind of, right? But if this guy is down, the problem that happens is you can't submit new jobs. But let's say that's not so much of a problem, because in production it's not like every minute I'm submitting new jobs, like as in the whole topology, right? But once this guy is down, if this whole node goes down, let's say one of these nodes goes down, then this Nimbus is actually responsible for restarting this guy somewhere else on another node, because the whole node failed. And so if a node Nimbus is down and this whole node fails, then you are kind of busted, because no one will go and restart those workers and supervisors on a different node. So as long if Nimbus is down and none of these nodes went down, then you are still safe. Things will work well till you bring back up Nimbus. Okay. All right. Back pressure. Storm has no back pressure. So the scenarios that I talk about, it happens, any of those things could happen. Do you have a unified programming model, non-overlapping model that we talk about? No, you don't have that. All right. Okay. So the thing is, there's another project called Trident, but many people consider Storm and Trident the same thing. It's one project within which you get a batch API and a streaming API. So Trident, what they did was they took Storm and said let's make it stateful, right? As well as let me give you batching support. So the batching support also came from a context of let me give you better processing guarantees. Exactly once. Can I get to that? So what they actually did in here, and this is showing you an example. So the Trident API is nothing but you still have spokes and bolts. Nothing changes. It's like you can say a layer on top that's reusing the same architecture and everything. So this is a tweet program rather than a word count. So I have here a spout, that's the Twitter spout. I'm taking each of the tweets, breaking each of the tweets, and within that taking the hashtags, and then I actually do an aggregation. When it comes up, you have to start from scratch, which you can't do in a streaming application really. So they've introduced this new thing called persistent aggregate, where you can store your state as messages you calculate, store it in a persistent store. Now that persistent store, in this case I've given you an example, it says memory map. So it's storing it in memory, but that memory is probably shared across multiple nodes, kind of a thing. So even if it crashed, you get it from another node. But they actually give you, like memory map state, you have an, you could write it to any of the other. You could write it to Redis, you could write it to, I think even a relational database, you could write it. And therefore, when it actually crashes, it goes back to that store and get it, right? So it gives you this nice feature of, becoming stateful. The only problem is that any persistence that he is giving you, statefulness, is actually going to an external store. And when you go to an external store, that means you're actually crossing the boundary. You have to write to a relational database. There is some latency and stuff. So people really, pick up on that, saying like, you've given me stateful, but I have to go to another system.
Excuse me.
Yes.
This is like you were saying, like replication. We used to do replication on different nodes, and here we are doing replication on an external system. Right?
Yeah.
So
You're right, if it's memory replication, if the other, I wouldn't call it replication. I just write to it. Whether that guy is doing a replication is his problem.
So like Spark, do we have a checkpoint kind of mechanism in Trident and
No, none that I know of. This is the only one that we have. So given that, Trident also has nice APIs. They've even introduced things like you can do aggregate, join, grouping, filter. So it's not like roll your own code. There's a nice API by which if you have two streams, you can join it. Like say a join, stream 1, stream 2. No, you don't have to write your own code. Great about it. This was the other thing that they tackled from in Trident. They've actually allowed you to get exactly one's processing logic. So the idea is that Trident is actually batching. So the interface doesn't change. The interface, if you looked on my previous slide, nothing changed. I didn't create batch interval and something. Guys who are used to Spark streaming, it says batch interval. In the previous program, I didn't set a batch interval. But there's a config property that controls how long he will wait, batch up those messages, and then process it. So your API didn't change, but internally, that's what he does. Right? So now, for each batch he generates internally, nothing to do with the application code. He generates a batch ID for each batch, right? And he guarantees that, let's say you had a source processing and then a result sync. He guarantees you that the ordering of those batches to the sync will always be in the order in which they were received, right? That much he guarantees. And therefore you will get exactly one's semantics, right? I think also when, this is just tied to that. I said, in these built-in stuff, both are tied together. When you are writing to a persistent store and he has built-in set stuff, like you could write to Redis. I'm not too sure whether you could write to Mongo or a relational, but he has a bunch of, like how you have memory map states for different external stores, he has that. So those two, and that also is ensuring that the write is atomic, right? We talked about it, right? Because now data is going across two systems. When I wrote, that system received it and crashed, or he received it and saved it and then he crashed. Those problems, those small window problems come in. But these implementation here for the built-in external stores, he's ensured that his written logic that it's guaranteed to be atomic. You don't have to worry about it. But if one of these external stores is not supported by the API, then you have to ensure that atomic write. Can you run? These features are same as Storm, nothing changed, right? You can't run on cluster across. There's no back pressure, and the fault tolerance is same as what was in Storm. With that, it's almost an hour. I'll take a break, and then I'll get to the next two topics that I had in the session. So, hope you had a good break and I've not gotten too boring, and I'll try to wrap up the remaining quick. So apart from those features and whatever we saw, there was a paper by, and there's a URL in here. So when you get the slide deck, you can go to it. If you look at the bottom, This was a paper presented by the Twitter guys who use Storm a lot, and they've used Storm for many years, many of their production things, and they ran into, they started facing problems more about, debuggability of, their Storm topology when things go wrong, and basically resource usage, the ability to run multiple Storm applications on a shared cluster, right? And this paper, you can read it. I'm just going to skim through it, but you can go through it, and if you're interested in that. They ended up with having to run each Storm application on its dedicated physical cluster. Even 2 Storm applications in production, they could not, run it. And they talk about some of the problems in here, right? And I just try to get a gist of it. So the issue that they found, right? Each of the Storm worker is one JVM within which you run what they call multiple executors, right? And what is an executor? An executor is nothing but your spout or bolt, right? So one JVM process is running spouts or bolts of one topology only. It's not across multiple topologies. But within these tasks, each of these tasks might have different needs. Let's say this is a spout, this is a bolt, and one spout, needs to do a lot of logging. Another spout, another bolt doesn't need, logging disk, but he needs more memory. That became very problematic, and you couldn't even with the Nimbus specify that for each of my workers, I want to reserve so much, disk, CPU, or whatever, right? So each of these tasks might have their own, requirements on CPU and stuff. And as a result, it made the JVM very, that one JVM very, prone to problems, right? And because each task had different requirements, especially around memory, the only way you could do it, for instance, was for this JVM, you go and increase the heap size to huge, right? And if you did that, and let's say when this was running, one of your executors had a problem, and you want to figure out what happened, the normal thing, this is all Java code, you tell it to do take a Java dump, right? Because I can see what's happening. Now, because you had to make this JVM's memory so huge, because there was no proper isolation, when you kicked off the Java heap dump, right? The heap dump, because the memory is huge, heap dump takes long time, and the heartbeat doesn't flow back to Zookeeper. That Nimbus thinks that you died, and he will actually kill your process, right? So such kinds of things. The heart of their problem was basically the fact that your multiple spouts and bolts are running inside one JVM process, and managing and debugging that was a huge problem, right? So what they actually did, there's other things. So if you look at that diagram that I had in the previous thing, and I'll go to that, right? Now as message comes in, right, for it to get into a task and then get to another task, maybe inside here or somewhere else, it actually has to, within this there are 2 threads, within this guy there are another 2 threads. So it actually has, each event has to float to 4 threads to actually go, and that's a lot of overhead, right? And I talked about the other thing, right? Yes, that entire JVM process across all your tasks, processing tasks, share the same log file, right? Same message passing queues. So if you have one task that is misbehaving, right, that whole worker is like kind of gone, right? And when you restart it, it might get passed to, when the workers get recreated, those 2 tasks might not go into the same executor as last time, right, when he lays out the topology. And then how do you debug the problem? So it was running, right, it had a problem, that particular topology. The most simplest case is, okay, you say I will kill it, and when you restart it, I still want to debug that problem elsewhere, but now, those 2 tasks didn't come together in one executor or one worker process, and therefore, I can't even reproduce the problem scenario, right? We talked about this problem, we talked about this. we also talked about this, right? And the end result was Twitter, for each Storm application, they had its own dedicated physical cluster. And when that application was taken out of production, you have to dismantle that cluster. So their cost was very high, and you had to even what can you say, allocate a lot of memory when you are saying this cluster of machines, how much they need, because the costs were huge. So they tried to do a couple of things, right? One of the things they did was they tried to make Storm run on Yarn, but they had some problems. They tried to do some other things. The paper talks about it, right? But in essence, what they finally did was they have so many applications that run on Storm, right? So they couldn't come up with a new system, because then you have to, with a new API and stuff like that, you'll have to port all these applications, which again is going to take years. So what they did was they kept the same API, but an implementation, they came up with a new implementation. This is called Heron. It's not open source. So they've just published the paper of the architectural concepts, of the problems they faced with Storm, what they changed and why they changed. It's not open source, so you can't download and play with it. But the paper is available to read. They knocked away Nimbus. There is now Aurora, which is their own scheduler, but equivalent to Yarn, so you could share across this. But the main thing in here was they simplified this. Each of your tasks that you call a spout or a board, each is one JVM process. So it's much easier to maintain, debug, size the cluster correctly, and control stuff, right? And then they simplify the stream manager of the communications between inside a worker, how the communication happens. I talked about that 4 threads of message going through was drastically simplified, right? They also talked about, like in the previous one, Zookeeper became a bottleneck, because as you made the your topology more parallel, all these guys have to keep, coordination is via Zookeeper. So now if you have 100 nodes or 200 nodes within a topology talking to that Zookeeper, then Zookeeper becomes the bottleneck, right? So they did some changes even around that kind of thing, right? So kept the API same, did a different implementation. There's a paper that talks about it, and their thing is that now any new streaming application that happens in Twitter is on Heron. It's no longer on Storm. Storm has been like deprecated, right? Okay. How many of you have heard of Flink? Okay, quite a few number of them. So Flink is it's a project that even started a little earlier than Spark, I would say, right? But Spark has got a lot of momentum. Flink inverts the model, as you see, right? They started, it's a continuous operator model, so it's a streaming system, it's not a task scheduling, but on which they have built batch on top of that streaming model, right? So they inverted the model and they did it. There are a lot of questions about that, right? So of course, streaming will do well if you take it, right? Does batch do so well on a streaming model? I think answer is not yet out there, right? It will take some time to come over, right? But the true thing in Flink, if you go back to these features, claim true streaming, right? But if you look at how you control latency versus throughput, you always recall, like, if latency is good, you're going to penalize throughput. But throughput is like how many messages in a bulk I can process through the system, right? And as you increase throughput, you penalize latency, right? So how do you control that? And there's a link in my slide at the bottom. When we share it, it will be there. We talked about the continuous operator model. So buffers are basically flowing across each of these operators. They allow you to control how long to wait before the buffer is shipped. Right? So in a way, you can even do micro batch, right? And you control that based on time, right? So they suggest that you could set each of those buffers wait for messages. You can set it as low as 2 milliseconds, right? But if you want throughput, then you set it to a larger, right? So theoretically, you could question that, like, is it really per message level versus is it some kind of a micro batching kind of thing, right? But even though they are continuous operator. If you have looked at Flink and you looked at Spark, you looked at those APIs, that's very similar. They're kind of almost competing with each other, right? So yes, they are stateful. One of the things that seems lighter the way they checkpoint. So we talked about this was like stateful and fault tolerance and exactly once. How do they gain it, right? It's not really a checkpointing thing. They actually, as the messages flow, they flow, as the events flow through the system, they flow what is called a barrier. And when the barrier reach the destination, it means messages that were before the barrier are already processed and I don't need to replay them in case of a failure. So it's lighter. One thing to remember is we are talking about all the open source streams. I forgot to mention. IBM has IBM streams, enterprise grade, true streaming and stuff, right? But for this talk, we are not covering that, right? And many of the things that is there, Infosphere streams does, right? Built-in primitives, yes, we saw Trident and Storm didn't have that, but Flink does have it. So these we saw with Trident you could do it. I think Trident you could do Windows, I'm not too sure about that now. One of the things that they also allow you to do is, I talked about in Storm, right? There's no statefulness, but you could build your own state. The question was, when I crash, I lose that state, right? In case of Trident, for the built-in functions where you do aggregates, that's automatically stateful. But let's say I'm doing my own computation like Storm because I needed to do some custom computation that there wasn't a built-in operator. I store that in a variable. I can even, as part of the checkpoint, I can say checkpoint my local variables. So that's a nice thing that I have. They do have windows, so you could have a sliding window or a tumbling window. Sliding is where I slide as things move. Tumbling is I do chunks. They also have this thing called a window trigger. So by default I can say my window time, say 5 seconds. But for instance, if there is a sudden surge in data, like events increase more than 200 for those 5 seconds, I want you to still close the window immediately, kind of it, right? So those things also you can do, which is a nice feature, right? The one other thing that they have is most of these streaming systems that we talked about, we never talked about this feature, is what is the concept of, when you create a window, what is the concept of time? Most of the time, the time is based on my processing system, right? So I'll say 10 seconds or whatever time is, or even the message that I got the time is based on my processor time. But if you're getting data, let's say from an IoT sensor, that time, the event happened there, that time doesn't correlate to your processor time. And more importantly, while messages flowed from your IoT into your streaming system, there's latencies in the network, right? Some event that actually happened later, a few seconds later, might arrive before the event that happened earlier. So how do you account for that? So I'm taking a batch window saying 9 o'clock to 9:05 and I do a count, but in that window, that's the window is the time, my processor time messages came to my streaming. That's not necessarily in the IoT when 9 to 9:05 was a different time, not this time, right? So what they've allowed you to do is, let's say at the IoT sensor itself or the device, it timestamps the message, right? And when it reaches into my streaming system, when I create my windows, I'm creating my windows based on the time of the message that came in there. So that way I guarantee that when I'm giving you counts, I'm giving you the real time, not the processing, right? A simpler thing is when I'm running my streaming program, I want to do like machine learning. I want to, maybe I've even trained my model up ahead, but as I do it, can I update my model and do predictions based on data that I've seen now, right? Can you do that with your streaming applications? Yes, you can do that, right? There's a particular method called map by state where you can build your model and you can do that, right? So these are some, as we go higher, you see the level of abstraction gets nicer, right? In Flink. Message processing guarantees. Flink does support exactly once, right? You could do it. Of course, you're assuming a reliable source. I talked about if I'm writing to, and if I'm keeping that my computations only in Flink or only in Spark Streaming or Storm, then exactly once is slightly simpler. But if I'm writing to a different storage, I have to ensure that atomicity. They have built-in support for exactly once with HDFS. So if you're writing destination to HDFS, they already provide exactly one's writer, so you don't have to worry about across these two systems atomicity. Flink's processing model, I said it's a continuous operator model. So you have something called a job manager, right, who's sitting, and then you have these each of these task managers, right, that run. And these are the guys where the code that you write, right, even on the higher API, right, like your map jobs or that are running in here, right. And as he receives, one of this could even be a source guy, so he's receiving data. As he fills up his buffers, he talks to the job manager and says, I have data. The job manager knows who's the guy, the destination for that processing, the next stage. So he calls that guys and says, data is available, go and take it. So these guys pull messages. But they kind of build up buffers that they are ready to transfer, and the communication still happens via the job manager. Right? Next slide is actually breaks it down a little more. What happens inside a task manager? You have something called a slot. Right? Slots are, you can think of it like an executor similar to slot, right? But within that he's actually running, this is a one task program, right? So some of the things that he's showing here is like parallelism, right? Which is not what I'm concentrating on, right? But you will see within a slot he's still running a source, each of your tasks, right? And you can split them, which is what is showing. But the question that I'm going back to is, you saw Storm had this problem that he says within an executor I ran multiple tasks, right? So my thing is, once this guy goes a lot into production, he's probably going to face the same problem as Storm, kind of a thing, right? To be seen, right? The same problems that the Twitter guys faced with Storm over many years after Storm served them well, right? But that's it. Fault tolerance of the master. So the workers, everything, if it crashes, as you saw even in Storm, they get restarted. Since we talked about Nimbus, who was the master not being fault tolerant, I just put this here. Fault tolerance of the master in Flink, yes, it's there. In 0.10 only. Prior to 0.10, even their master was not fault tolerant. Back pressure, yes, Flink streaming system has back pressure. I talked in my original slide of there are multiple ways by which you implement back pressure. Flink's back pressure is that is basically the buffer that he transfers across those nodes that I showed you has a watermark. So he will not fill it up more than 70%, let's say. And then unless the destination guy pulls some data off that, this guy is automatically going to get throttled. So that way back pressure works there. He is not actually flowing messages between the components to tell slow down, but because he has a watermark, back pressure applies. Does he run on shared clusters? That's even covered there. Yes, he has an overlapping model between. So Flink also has a batch API. It's called the table API, right? Last when I looked, it didn't have SQL support. I'm not too sure, but I might be wrong. But for definitely the batch part of Flink is not as evolved as Spark, right? And so equivalently even the graph and the ML part, right? On the streaming part, I would say they are strong. But if you are looking at the other things that you need, use it as a platform. My take right now from reading the docs is on the other ones they wouldn't be as as good as Spark. Spark streaming, again, I'm not going into details because there was a session where we covered that. I'll just go through it. Spark streaming, we saw it's micro batching, right? It's not true streaming, right? The question is how small can you create those batch windows? And I think Sachin has some stuff of not how much you created, but some of the work that we are doing that will give you some ideas. Yes, it is stateful, right? They have functions like update state by key and map with functions that keeps the data inside Spark but stateful and guaranteed to recover in case of a failure. Built-in primitives, it's there. Sliding windows, train models and predict like we saw, same thing. I said this map with state is what Flink has. In 1.6, even Spark streaming happens. Event time is not yet there in Spark streaming, but 2.0, which is supposed to be 2 months from now, it's slated in there. So then you match up on that, right? Message processing guarantees, yes, as long as your source is exactly once, you can get this exactly once. Do I have built-in, guys, when I'm writing to external stores for exactly once? It's not built in there. Like we saw with Flink, the HDFS exactly once, it's not built in, but you could write your own and then show it. But probably they will build that up. Run on shared clusters, yes. Back pressure, yes, streaming has back pressure. Spark streaming, the way he does back pressure is different, right? Different from Flink. So what happens in Spark streaming is, I know my batch interval, let's say, is 5 seconds, right? So every 5 seconds, I also know how many messages I put in that 5 seconds window, right? And I kicked off the job, right? And I also know how long that job ran. Let's say my window is 5 seconds, and the processing of that 5,000 records took 6 seconds. So I know it's not matching. So what Spark streaming would do is that when he creates the next window, when he's taking the source data, he will say, you have to take less than 5,000. So we cut it, let's say, to 4,000, and he checks the time that took to run. If it was too less, then he would increase it between 4,000 and 5,000. I'm just giving a scenario example. But that's how he builds out, back pressure. The question that you'll ask is, are you dropping data in that case? If you're using Kafka as your source, Kafka has persistence, so yes, so you don't lose data. You can always process. But yes, your latency is dropping. But the thing is, should the system crash because you overloaded the system, the chances are it gets unstable, right? You want a stable system. So he guarantees that's stable, and you have persistence. Then I talked about dynamic allocation, right? If you're running on a cluster and there's no more physical nodes, because you're doing dynamic scheduling, right? He can probably apply back pressure and then also apply dynamic allocation to increase more nodes and partition it more, so that it brings you back, right? So your latency also will, it's not that the messages are getting queued up in Kafka. Once I can allocate more, you'll come back to a stable system and processing at the latency that you want. Yes, dynamic allocation is only there in 2.0, not yet. Fault tolerance of master, it's there. It uses a checkpointing mechanism. So, the D stream is checkpointed once, each job finishes. The D stream state that you need is checkpointed. And if the master fails when you restart, he will start from the check. Programming model, yes, there's an overlapping programming model. Is it as great as Apache Beam? Maybe not, right? But you have that, and the fact that you also can integrate your streaming application with, we talked about it, doing MLlib, train your model and stuff. You could write SQL queries to another RTD. All that is there. So definitely a great platform. So this is the final slide that summed up, what we took at. If you look at, yes, you'll see most of the yeses are on this side of the house, and more of the no's are on this side of the house. I won't go through them again because we've already done that. And with that, I will hand over to Sachin to talk about a little of the work that we've been doing, our experience on trying to do some benchmarking on Spark.
Is it audible? Okay. So we decided that we will do benchmarking of Spark with other systems. So this is our first part of it. In this we will discuss how we are planning to do benchmarking of Spark. So we decided, okay, let's explore the Spark, how Spark reports on the UI of the Spark. So they internally maintains a streaming listener. So in this streaming listener, they internally have a streaming listener interface. In that interface, they have functions like on receiver start, on receiver end, on job start, on job ends, on batch submitted, on batch completed. So what we can do, we can write our own class, extend this class, and we implement all these functions. And in those functions, we can say to the Spark, okay, what you have to do when a batch gets completed, or when a receiver gets completed, or receiver starts. So in this case, we have done our own, we have done a project setup, and we have all the scripts in the GitHub. I will post the link of the GitHub in the meetup page. And in those scripts, what we do, we start a Kafka cluster, we start a Spark cluster, and then we have one load operation which loads the Twitter feed. Okay, this load operation loads the Twitter feeds and dumps into a local file system right now. We can make it to SDFS for like replication, use those details about it. Then once we have a fixed data set, we are using this data set to stream it into to push it to Kafka, then to Spark. And we are controlling knobs there, what's the rate of the data that we input to the Spark. So based on that rate, we can control like how much data we want to push it in 1 second or one batch of the Spark. Once the data is there in the Spark, we use this interface. Whenever a batch gets completed, we dump the data, we dump all the metrics we want to calculate. And similarly, we are planning to do for Flink also. So same data set what we have dumped from Twitter for Spark, we will do for Flink, and we will compare the metrics. Right now, we have done only first part of it, like how to benchmark in the Spark. So, show you the code. So in this, the project is organized like this. We have a Flink project, we have load data project, we have push to Kafka, and we have Spark streaming. So if you go to load project, it is a simple program which connects to Twitter and pulls all the tweet, and it dumps into one file location. So where we are using same Spark code also to do this. So we make connections in all the executors, and all the executors will pull from Twitter, and will for each RDD we have used here, and inside for each RDD we are dumping this after repartitioning. We are repartitioning to create one file per RDD, so that we don't have so much files to maintain. And so once this data set is ready, we use this data set as a static data set. So if you are using the same code to run in your use case, you can modify this load data and use it for your use case to dump the data in the specified format you want, or you can create a dummy data itself here instead of pulling it from Twitter. Then we have push to Kafka. In this push to Kafka code, we are using threads. So we have a thread count, how many threads you want to spawn. So this thread count will be our tuning knob, how much you want to put it in 1 second. And we are reading buffer source. We are reading this data source that we have right now. It's local, not SDFS. So we are reading that line by line, and we are pushing it into Kafka with partitions. So we know how many partitions are there in that topic. We use that information and we distribute this on all the partitions. Why we are using this information is because the direct Kafka implementation in Spark uses this Kafka partitions as the default partitioning mechanism inside the Spark. So if your topic has less partitions in Kafka, the Spark will have less partitions inside the RDD. So if you want to increase the level of parallelism inside the Spark, you have to increase the partition inside the Kafka with the direct Kafka implementation. If you have receiver code, in that case, the tuning knob is batch interval, block interval. So batch interval is your batch which get processed, that will be your one RDD. Within that, how many block interval fall in, that much will be your partition. So in this case, we are using the Kafka partitions as the default partition mechanism for Spark. Now we'll go to our main code, which is our Spark code. In this Spark code, I'm reading conf variables in the top. The code is very simple from here. So what I'm doing right now, I'm creating Kafka params. This object we will pass to create direct stream object, and we'll use the inbuilt mechanism inside the Spark to Kafka utils.create direct stream to use this. We got the messages. Now we are doing map operation on that. So this code I have explained in the previous Spark meetup, and I have gone to step by step. So you can check that out. So in that case, what we were doing, we were printing these tweet counts. So what it does, it last 60 seconds, it will print top 10 tweet counts. So now we are not printing it. We don't want that to add to our benchmark, like processing time to that. So we have a map, we just write it to the map. or we just flush it. We don't store this information. We don't waste computation in doing that. So only what he is doing, he is reducing each window by key. So that means you have a tweet, filter it for each hash counts. Now we have hash 1, hash 2, hash 3. Now count them as a simple word count. We did a word count on that. Then we do take first time, and then just drop this list. It's not, the action right now here will be like we are doing set map. Inside the map we don't maintain the copy. So this is what implementation we have done for performance metrics is this part. So this is our latency listener class. This extends the streaming listener thread. So in this there are, if you go to streaming listener code, in this they have different functions: on receiver start, on receiver error, on receiver stopped, on batch submitted, on batch completed, batch started, and output operation started and completed. So you have to override these functions. What we use for our use case is only on batch complete. So what we are doing in this is we go to the batch complete part, or whenever a batch gets completed. So either it will, we have divided into first batch, or it is a batch in between somewhere, or it is a last batch. When it is a first batch, that means first time we will see number of records more than 0. Okay, so when there are number of records more than 0, we say record the start time. We are taking start time at that point of the time. Then in intermediate batches, we only store for the like to observe the behavior when it's going up and down. But for this case, we only interested in the last, when it ended. So we broke down our metrics into 2 metrics right now. Only 2 metrics, like average records per second, which Spark gives us, that we can treat as throughput, and average latency per batch. So in this case we are considering only 2. So whenever there is a batch which is not the first or last, we just update the batch count and we update the total records. We update the total records just to get to identify the last batch. Whenever is the last batch, how will you identify? So our last batch is whenever our limit reaches. So we say we are processing 100 million records. So whenever 100 million records, just stop the computations and give us all the metrics. So the criteria to identify as the last batch, we have kept like total records greater than equal to record limit. At that time he stops, and at that time we record the end time. So we have start time, we have end time, we have total processing time, total delay. So we can add like total delay by total records, we will get the average latency. And for throughput, we say total records by total time. Okay, so there is some mechanism of total delay, how we are calculating total delay, which you can see it from code. What we are doing that, okay, one batch got delayed by 400 milliseconds. Then every record in that batch got delayed by 400 milliseconds. So record we multiply by that delay that batch had. That means we got the total delay. Now if you divide by records and then you do an average, you get average latency by batch. So that I think if I explain it will go pretty fast, but if you see the code you can correlate it with what I said. So what we have, same map we are using here, matrix map. Okay, now we have a setter method and getter method for this map, and we have we take batch size, record limit per thread, and how many threads are running. So for every experiment we can change the number of threads and number of limit per threads, so we can control the like input rate to the Spark. Now from this we got our record limit, when to break. So now we have on batch implement override method of this. In this we have a batch completed object. So in batch completed object we will find a batch info object. So batch info object is set for every batch. So this contains information for each batch. So if you want to get an information for every batch, you can use this batch info and say batch info dot number of records. Or if you see here, we have like number of records, what is the processing delay this batch had, what is the scheduling delay this batch had, and total delay for till this batch. This is our added parameter. And the batch time, what is the time that batch had got created, like every 200 milliseconds. They have a Spark has a separate timer that kicks in that timer to create names for each batch. And processing delay. So this code we use to capture when we want to know for every batch. We want to capture every batch information. Otherwise we will skip to this. We have updated here total records with the records this batch had. Now we'll go ahead, total records greater than record limit. Then this is our last batch. Whenever is a last batch, we go into this batch and we record the end time. and we say the end time minus start time, we calculate the total time, we calculate average latency, and we calculate the throughput from here, and then we store them into the map and print it in the last. And how we stop at that point of the time, we are using this thread for that. So this thread is a simple, this implements this stop context thread. In this we have only one command which says ssc.stop true, and so that it stops gracefully. So it processes all the data which has in the memory at that point of the time. So we kicks in this thread and we prints the, before that we print the map. So we maintain this map for all the batches, or you can just populate this map for the last batch and we print that value and we just exit this code. The place where you find how to calculate total delay. So there we are calculating total delay by the value within this batch into the records this batch. And then this total delay is divided by number of records in the last to calculate the average latency. So this is one simple class you can use to get metrics from the Spark. You can add your custom code in this and you can change these classes. And what we have observed till now, so we started executing with different batch size. Is it visible? I don't know how to increase the size. So we started with 1 second batch, 2 seconds batch. So when you do 1 second batch, 2 second batch, our processing time was 400 milliseconds. So when you have processing time 400 milliseconds, 1 second batch goes smooth. You won't have any problem. The time batch gets started, previous batch is finished. So it goes easy. Then we start, we will see a unstable behavior. We started decreasing the batch interval. So we went to 900 milliseconds, 500, 600. But when we hit 500, our average was 400, but sometimes it goes above 500. At that time, suddenly we see a behavior where the Kafka offsets that he gets, the data that he gets is within a batch, keeps on increases linearly after once he hits this point.
You want to say that we didn't turn on back question?
Yeah. So we have not done any customization on configuration part in Spark. This is raw Spark. Only that we have done is we have decreased the retry times. If any retry happens, we want it to fail. We don't want it to waste time in retries for the benchmark. So this is the raw Spark that you download. You start on that. No customization, no extra settings we have enabled in it.
How many nodes in the cluster?
This is 9 nodes cluster and 3 nodes Kafka cluster separately. And we have 48 processing cores on each machine and 128 GB RAMs. So when you decrease these time slots, and at 500 time we hit first place when this unstable behavior kicked in into the streaming cluster. What happened at this point of the time, that processing time increased the batch interval. Once the processing time increased the batch interval, if you see the Spark UI, the input rate that it reports within a second keeps on increasing because the data got piled up from the previous batch. And it's a linear increase. After that, your cluster gets worse and worse. You won't be able to recover. So if you see from the numbers, our average delay from this point started increasing back. From 500 milliseconds, it started increasing instead of any impact on the processing average delay. So we thought this is at one. In this case, our input was constant. Every time we are giving same input. Now we found 500 milliseconds with 400 milliseconds processing time at some input rate of say 90,000 records per second. Then what happens when we change the number of records for this same batch interval? Then we changed the experiment. We kept the batch interval as same 500 milliseconds, and every time we are using different input rate. So if you see we started decreasing it. So we had 60 threads initially, then we keep on decreasing 60, 50, 40. So again, if you see with the 60 threads, it went fine. No, 60 threads we had the same unstable behavior. So we keep on decreasing the input rate. So where we find some, so after when we had 24 records, 24 threads, approximately 66K records per second when we were pumping into the Spark, at that time we started seeing the same stable behavior. So it's not only the processing time and the batch interval which is a parameter here, the input rate that you are pumping in, because your processing time also depends on the input rate that you are pumping in. So they also depends, like when your cluster becomes unstable. So right now we have this much observations, like in this case, one major point that we find out, once your unstable behavior kicks in, there are two times that you have your batch time and you have a schedule when the batch gets scheduled. The gap between them keeps on increasing. So with 100 milliseconds, we have seen a gap of like 7 minutes when a batch got created and batch got scheduled. So there only we have that much delay. So the latency keeps on increasing at that point of the time. So we are exploring that why there is a difference between that and why we have less number of, there are second observation we have that is batch count is decreasing. So if batch count is based on time, why the batch count should decrease when our total consumed time is equivalent? So if we say that our processing is running for 1000 seconds, then if you have that should be equivalent, batch count should be multiple of total consumed time divided by batch time. It cannot be like it's a random that it decreases. But with the direct Kafka, we are seeing that the batch count is decreasing because he combines, like he uses the offset at that point of the time when batch gets scheduled or batch gets started executing. He fetches offset at that point of the time. So at that point of the time, we have pumped in more data. So Spark fetches more data and he takes more time in the processing, and it gets worse in the next batch and it gets worse in the next batch. So if you are running some system right now, so what you can do, you can tween these two hooks. One is batch time, another one is input rate, and you can find out an optimum for you that you don't hit the unstable behavior. Once we have more information on these parameters, like how to tune these, in the next meetup we will present those, and we will present the Kafka, Flink numbers also.
So input rate you are controlling with the number of threads, or?
Yeah, input we have 48 cores on one machine, so we can go up to like 50 threads per machine and 3 Kafka nodes where it's running. So 150 threads we can go. Right now we are only using 60 we have gone.
But how much, I mean, the number of thread doesn't, I mean, how much cache your system is having, that's also depend.
So in that's an isolated system, and only one process is running at that point in those machines is loader. And the loader is taking 128 GB RAM fully provided for the loader.
128 GB RAM is there, that's fine. But how much cache is your machine is having? Because I mean, there's a reason I don't know completely, but I mean, just increasing the number of threads doesn't mean that processing will be multiplied by that number of threads. For example, if the system has 10 threads,
so
doesn't mean that
there is a point where we will hit that. Right now we have not hit. Right now, if we increase the thread, our input rate is increasing linearly.
No, because cache storage will be there.
That's it.
If
So
something data is in a cache or something that is.
Yeah, that's what I'm saying, that we have reached up to 60 threads and we have not seen that behavior. I got your question that it won't be linear after some time.
Exactly.
So we have scope up to 150. We have reached only 60, and let's see when we kick in that. At that point of the time, we have to find one. Either we have to scale the cluster or we have to find another ways of pumping the data.
No, my question was different. Like, even forget about linear increasing of your performance. Forget about even in the performance, what you are getting is not linear. I mean, suppose at 10 threads you got output 100. In 20 threads you will not get 200. You will get some like 170, 180. This is what my question. Even the performance you are getting is not linear. I mean, once it will decrease, that you are aware of. But even within wherever.
Now the difference is very less, so we can, for our analysis, it's fine.
I think the other one is, we are not yet put is like, on those machines, you need to look at what your CPU usage, what your
so that's our second step, like we are going what experiment we did in this state. Are we able to utilize the cluster, or cluster is a bottleneck somewhere? So if we are like monitoring now CPU usage, network usage, memory usage, and all of these numbers we will bring in the next follow-up of this. So
by default, Spark has got its counters, right? It has got the CPU, memory, and other.
So we want to use from the machines instead of the Spark counters.
So we can have another solution, like if I'll talk from very bottom line. Suppose your input rate is so fast, processing is very, means compared to input it's a slow. So we have delay in processing, right? in that case we can have persist or
So right-
cache. Here you can utilize memory. Let it come, dump it.
So ultimately what we want to see is latency. So if you persist it or it is in Kafka, you fetch it at when you need it. So it does not matter whether you are persisting towards Spark, you are adding a code in the Spark to persist it and control it, or you leave it to Kafka to do it. Ultimately you will suffer in latency. So what we are measuring here is whatever, leave it to Kafka and measure the latency part and say when you pumped in the data to the Kafka and when you got out of the Spark, what was the latency at that point of the time?
I think the biggest question, if we looked at the previous slide, when someone's picking Spark streaming, the first question they're going to ask is, if I can live at 1 second batch interval or latency, there's no you don't need to make any decision, you can go to Spark streaming. The question will be when you are having apps that you need much lower latency, right? Can the task scheduling overheads be so low that you can still go to it? So that's basically the question trying to answer. And that's the question that we get asked also. When someone comes and asks, okay, what's the minimum latency that you can support in Spark streaming? Because it's micro batching, right?
So it's like you cannot say per use case, like for this processing time we can have this much batch interval, because the input rate also kicks in, and based on those two parameters right now you can decide it.
But then, this side, right?
Yes.
I mean, suppose, just a basic computer thing.
Yeah.
Suppose you are pushing number 1 to 10. So the 10 numbers are different. And suppose you keep on pushing number 1 10 times. So this is different because again this, what thread you are talking about, it will get the cache things. It will always store number 1 in cache and then keep on giving. So in this case it will be faster.
No, in this case all the threads read their own files.
No, I mean to say the data inside the file. Data inside the file, because it stores somewhere finally, right? Inside the RAM after it stores in the cache also. So the cache miss and cache hit, the two things. So if the data is different, suppose we have 3 names, A, B, C.
That's why we are not focusing on varying processing time.
That we will go to in that
Processing time in all our experiment remains same, because every time we are pumping in same data. We are not pulling data from Twitter every time, different data. Our data set is static. So if data has some randomness, it's there. If data does not have a randomness, it's constant for all the experiments.
It's local things.
Yeah, it's a local thing. It's just static. So
to this question, I think the point that you were driving to, if you're comparing it to some other system, you want to ensure that the operating system caching of data and all is consistent across the board. Otherwise, then you're penalizing one system versus another. That point is taken.
So for us, what we thought, okay, this static data we will use for everything. The same loader we will use, the same Kafka setup we will use. So we are not differentiating between the systems based on this.
I think we're already at 12:10, so if there are questions, we'll take. What's the mic? We have no mic runners.
My question is like what he said. Pawan is his name, right?
Mario.
So my question, like the person comes and asks you, how did you benchmark, right? You said, right? So some person comes and asks how much delay, because the batch processing thing is back. So how much delay support? So my question goes back when you say, okay, this is a benchmark, this is a delay we are supporting. So do you mention the kind of data also there, property?